So first of all, I would like to say thank you for taking time to watch my video. So my name is Muhammad Irfan based in Iswanizam, and I'm currently a final year student finishing my bachelor's degree in electrical and electronics engineering. And for my final year project, it is titled The Development of a Loose Fruit Collection System for Palm Oil, and a little bit of background of and a little bit of introduction for palm oil. So as we know, palm oil is a very lucrative industry. However, the harvesting, the harvesting and collection and processing of the palm oil is very tedious, as I've seen in my research and in the field. So what I can say is that the process of collecting this palm oil begins at the palm oil tree, and these palm oil trees are very tall, and the palm oils themselves are that must be harvested are at the very top of the tree, at the sides, the very top of the tree. Yeah. So the only method to collect them for harvesting is to cut them from the branches and to make the palm oils fall down to the soil. And these palm oils are contained in what's known as fresh fruit bunches, where inside these bunches are these fruits, and these fruits contain the high concentration of the palm oil themselves. It is these fruits that we want to extract the oils for the business, for business. So, when these fresh fruit bunches fall to the ground, some of the fruits that are contained within these bunches, they separate from the bunches, and they scatter across the tree. And these scattered tree fruits are what's called as the loose fruits. And these loose fruits, as you can see in the proper statement, they have high economic value for upstream production of palm oil. And failure to collect all of these will cause a loss of millions of ringgit from the total revenue. Why is this? Because each fruitlet contains a high concentration of oil, and hence workers need to collect each of them in a short period of time. And thus, it requires a workable mechanization to improve the collection system, the collection period. And currently workers have to manually pick up each fruitlet by hand with limited tools, and it is considered inefficient and time-consuming, as well as more workers are required to do it. And thus, from the problem statement, we can determine the objectives of this project are: firstly, it is to investigate an optimal feedback system for the loose fruit collection system. Secondly, it is to develop an autonomous loose fruit collection system integrated with the ROS programming code of the autonomous robot. And thirdly, it is to test and verify the performance of the autonomous robot in real-life palm oil plantation. So for the methodology, here we have a broad diagram of the loose fruit collection system, where the brain of it all is the Arduino Mega 2560, which powers three systems: the roller system, vacuum system, and separation system. This roller system is main role is to collect the loose fruits that are scattered across the tree. How does it do that? It uses linear actuators and also digital infrared sensors or IR sensors. So the autonomous robot currently uses two IR sensors and one linear actuators as the roller system. The two IR sensors are used as to detect the distance of the roller from the ground. So, for example, when the IR sensors detect that the roller is too close to the ground, it will send a signal of 1, which is high and high, which says that both the left and the right side of the roller is very close to the ground. Thus, it will then send a signal back to the linear actuator, telling it to raise the roller. And thus, vice versa can also be said when the IR sensors detect that the roller is too far away from the ground. And thus, this closed loop system is key to creating an automatic system of efficiently collecting the loose fruits. And then next we move on to the vacuum system. So once all the loose have been collected, they will then need to be conveyed to the vacuum system. And this method of conveying the loose fluids is accomplished by using this power window motor. This power window motor, which is typically found in power windows in cars, we use it to power up the conveyor belt, which functions to transport all of the loose fluids from this roller system into the vacuum system. And how does it work is by the loose fluids are then conveyed to a vacuum tube, where this vacuum tube is sealed, and then once it has been conveyed there, three brushless DC motors, which are rated at drawn motors as drawn motors, it will then create a suction power to suck all of the loose fluids from the roller system and place it inside a chamber for further processing. So once all of the loose fluids have been collected, it will then move on to the separation system. This separation system is the system which functions to act as a filter to filter out all of the loose fluids with the attached debris and unwanted materials. So how it functions is it uses one linear motor actuator and two inductive proximity sensor. This inductive proximity sensors functions the same way as IR sensors, only it only detects metal surfaces. So for in our case, we use these two inductive proximity sensors and one linear motor actuators to control the closing and opening of the chamber lid. So for example, when all of the loose fluids have been stored into the chamber and we want to move on to the separation system, we will then send a signal to the linear motor actuator to open the chamber lid. And once it is fully open, the metal proximity sensor will then detect the metal lid of the chamber, and it will stop the linear actuator. And thus all of the loose fluids will then drop into the separated drum, as you can see here, which will then proceed to the next stage, which is we use this brushless DC motor to ramp up and provide constant speed to the separated drum to spin, and this spinning causes the debris, unwanted materials, and anything else that might be attached to the loose fluids to separate from the loose fluids. And thus the end product will be these clean loose fluids that have minimal to no debris and unwanted materials. And thus we can move, and then these loose fluids can then be transported for further processing. And thus, as for the result and analysis of this of my project, here we have a real life implement. Here we have the loose fluid collection system circuit, where we use the components that we plan to use. For example, we have a power window motor, we have two linear motor actuators, one for the roller, one for the chamber, and two brushless DC motors, one for the vacuum and one for the separator. And also we have two digital IR sensors and two metal inductive proximity sensors. So for the analysis of this circuit, first we would like to analyze whether the system itself is operable, whether it is workable to be used in the real life or oil palm plantations, and also we would like to determine the total watts used for the system. So in the table to the right, here we have a table of the rated power compared with the load power. The load power is the actual power used for these components. So here we can see that the total rated power of the components, it is 290 watts, whereas the actual load power is only 52 watts. And it is also mentioned that the sensors are not considered in this analysis because the total watts used by each of these sensors are very low, and thus we can ignore these consumptions. And also we also compare the rated amperes and the load amperes of the components. And we find that the total ampere of the rated ampere is 25 amps, whereas the actual load ampere is only 4.3 amperes. And next, once this has been successfully analyzed, we can then implement this to the real-life autonomous robot Izzul collector system. So here we have the autonomous robot itself at the Sandabi Opa plantation. And thus we then proceed to test it out in the table to the right here, where we test it out for the number of loose fruits which we tested out in the system between two trees. And between these two trees, the number of loose fruits are set to a constant of 300 loose fruits. And we find that the most highest number of collected loose fruits obtained is 220 loose fruits, whereas the number of uncollected loose fruits is 80, and the debris is less than 50. So as you can see in this table here, we can see that there is a separation between 120 and 100 loose fruits collected. 120 here is representing that the 120 loose fruits were completely collected and separated, whereas 100 other loose fruits were also collected. However, it got stuck on the conveyor due to the muddy soil sticking together. This muddy soil is caused by the rainy weather prior to the testing day, and this causes the soil in our palm plantations to turn muddy and not a good uh, environment for testing our system. Thus, for the conclusion, we can conclude that an optimal feedback system for the loose fruit collection system was successfully investigated. An autonomous loose fruit collection system integrated with the ROS programming code of the autonomous robot was also developed. And lastly, the performance of the autonomous robot was tested and verified in real-life palm oil plantations. However, also I would like to note that this is still in research. This robot is still in research. It is only still 1 year. It's only been 1 year of research. However, some improvements can be made. Whereas, for example, in the roller system, we can remove the linear motor actuator completely and replace it by using rotary encoders. These rotary encoders can be used to more accurately control the position of the roller. And also by adding more IR sensors also helps to provide more sensitivity of the roller. So that is all for my presentation. Thank you for listening and have a good day.